In this next section, 7.1D, part 1 of 2 parts, we're going to look at using what is called an activity series table and then a solubility table. And from that, we're going to use that to predict products of single replacement reactions using this series. So we're looking only at single replacement reactions. Part 2 will focus on the double replacement. Real quick, what type of reaction is described by the following? 6 lithium plus nitrogen gas produces lithium nitride. Is that a synthesis reaction, decomposition reaction, single replacement reaction, or combustion? If it says synthesis, you're right. I got 2 things I'm putting together. I only got 1 thing on the product side. So I'm putting together to make a bigger product. Balance the following equation, indicate whether it represents a combustion, synthesis, or decomposition. Sulfuric acid produces hydrogen peroxide and sulfite. First off, look at your types of reactions. Is this a combination reaction, decomposition? Shouldn't even say combination, synthesis. We only got 1 thing on this side, so we're decomposing. The question is, which one's balanced? If you pick number 2, you'd be right. 2 hydrogens in, 2 hydrogens out. 4 oxygens in, 2 plus 4 oxygens out. 1 sulfur in, 1 sulfur out. Okay, predicting products of chemical reactions. The number of and type of reactants is a good indicator for the type of reaction and its possible products. So that's the overview we're going to have as we go through these. So we're going to predict basis a single replacement reaction at this point, an SR. A lone element replaces another element already bound in a compound. A lone metal replaces a bound cation. A lone nonmetal replaces a bound nonmetal or anion. We have what's called an activity series. We use this to predict products of single replacement reactions for metals. So we're exchanging metals. We use this. And higher up elements will replace lower up elements. So if lithium's sitting by itself and it comes up against like aluminum hydride, it'll kick the aluminum out because it's higher on the list than aluminum. So as I go down this list, the ability to react decreases. A lower one will never react with a kick out a higher one. It'd be a non-reaction. So let's take a look at that. Single replacement using a metal. We have calcium and copper sulfate. Since the lone calcium is higher on the reactivity level, it's a metal, than the bound copper. There's calcium on the table. It's higher on the table than the metal copper that's bound. Copper is much lower on the table. It will react. It will replace it. The calcium will replace the copper. You will get a reaction. So the calcium will go with the sulfate and the copper will be kicked out by itself. Single replacement with a non-metal. We have sodium bromide and chlorine gas. There is no lone metal in this reaction. We only have a non-metal, which is diatomic chlorine molecule. So it's not a metal. So I can't use the table we used in the other slide, but instead we use the periodic table in a previous idea. So here's bromine and chlorine. They're both halogens. Chlorine has a higher electronegativity. Remember, if I go from left to right, the higher electronegativity, I go from the bottom to the top, higher electronegativity. So the ones in this upper corner have the highest electronegativity. So it will react. There's chlorine. It's higher on the periodic table than bromine is. So there will be a reaction. So in this case, the chlorine will kick out the bromine that's bound up. And the bromine will be freed up. So you get 2 sodium chlorides plus bromine. So the bromine gets kicked out and chlorine takes its place. Another example of a single replacement with a metal. The lone zinc is higher on the electronegativity table. It's a metal, so I look for zinc. There it is. It's higher than the bound hydrogen. In this case, even though hydrogen is a nonmetal, remember it's on the metal side, so it acts as if it were in this case. There's hydrogen. That's why it's in parentheses. In this case, it's on this table, even though it's technically a nonmetal. It will react. It will replace it. So the zinc will kick out the hydrogen, and the hydrogen will be all by itself. Remember, hydrogen cannot exist as a single atom, so it would be a diatomic hydrogen plus zinc 2 sulfate. And a practice problem. We're going to identify this reaction, predict the products, and then balance it. So we got everything here. We got chlorine gas and sodium iodide. It's a single replacement of a non-metal with higher electronegativity because chlorine is a non-metal. It's by itself. This is the compound. There's chlorine. It's a single. There it is on the periodic table. I can't use the reactivity table because it's not a metal. It's going to kick out the non-metal ion, the anion, because it's lower on the reactivity table, or has lower electronegativity, I'm sorry. So a higher electronegativity will kick out a lower. If it was the other way around, iodine with sodium chloride, it would not react. So the chlorine kicks out the iodine, and the iodine becomes free. And since it's in group 17, it has to be a diatomic. So I have diatomic iodine plus sodium chloride. Sodium is now with the chlorine. I got 2 chlorines going in. I got 1 coming out. I got 1 iodine going in. I got 2 coming out. I have 1 sodium in, 1 sodium out. So I'll put a 2 in front to balance the iodine. So I now have 2 iodines to match the 2 here. That means I have 2 sodiums, so I got to put a 2 there to get my 2 sodiums to balance. That also gives me 2 chlorines, which balances there. And we're done.